Okay. So good morning, everyone. We will continue our unit 2. We are very close to almost determining the current characteristics, or what is called as VI characteristics. And VI characteristics, the equation is very important as one of the most important things to know about the transistor. How can we predict the current? That is the first thing, okay? And also, how can we increase the current? And as we will see when we come to the equation, we don't have complete flexibility. We have flexibility over certain terms as a digital designer, and that will be the way in which we are able to increase the current. And this is one of the most important topics of this whole course, right? If you have, for example, a transistor, like I said, we are trying to prepare you constantly to attend an interview in this domain. And one of the most important questions they will ask is, can you tell me what is the current flowing through a transistor? So before we go into that, let us quickly try to remember what we did last class. Okay. So the first thing that I want you to try to remember, we looked at different modes of operation of the transistor. There was accumulation mode, depletion mode, inversion mode. And in these three, inversion mode is the most important. Okay. Accumulation mode hardly ever comes because that is when we apply, that is when we attract majority carriers to the channel region. Depletion mode, yes, when the transistor is just beginning to turn on. But inversion mode is the most important mode of operation, and here the transistor is considered on. That is, the switch is closed, or the source and drain are connected together. And this could be for a PMOS or for a NMOS. Since we did NMOS extensively in the last lecture, I will just draw a PMOS transistor. Okay, this middle part is also called as the channel region, that is directly under the gate terminal. And in a p-type transistor, on the left hand side and the right hand side, the source and drain terminals, they are of type p plus. That is, there is a region that is fabricated, that has a lot of holes, right? And in between, actually, it is a traditionally a n-type substrate. But what we do is to turn on this transistor, that is to go from off to on, inversion mode. Okay, we apply -2 volts. How do we get -2 volts? Very simple. Just connect this to ground. That is the gate terminal. You connect it to ground. Okay, because like we've been saying, we don't have negative voltages as such. But relatively, that is with respect to one, another can be -2 volts. How do we get that? This is how we get that. Connect the gate to ground. Connect the source to 2 volts. So what is VGS? It is VG minus VS, or 0 minus 2 is -2 volts. And -2 is a nice negative voltage. So what happens is all the holes which are minority carriers in the substrate, because it is an n-type substrate, they all get attracted and directly they sit below the channel region, with the effect that source and drain now are looking like one continuous region, which means that there is a connection between source and drain. So these holes, they are not fabricated, okay? They are attracted by the negative electric field of the gate voltage. This is the most important thing. This diagram I have drawn, even though the source and drain look like they're connected, this is only temporary. If I go back to, instead of VGS equal to minus 2 volts, if I connect this also to 2 volts, then VGS equal to 0, which means all these holes will disappear and the source and drain are disconnected. So this is called as the inversion mode. We are inverting. What are we inverting? Inverting means make upside down. Here we are inverting the N-type substrate to a P-type region. Where are we inverting it? In the channel region. Similarly, when we were discussing NMOS, we were inverting the P-type substrate of the NMOS into a N-type region in the channel region. So this is very important, inversion mode of operation. And the second thing, which is again related to this, is the threshold voltage VT. Okay, so this is a number. It is a voltage for a transistor, and this is the number that is defined for either a NMOS or PMOS. In particular, it is the amount of voltage I have to apply here, okay, such that the number of electrons or holes attracted in this region, the concentration is the same as the substrate. That is, substrate will have some concentration of majority carriers, maybe 10 power 15. Now I have to attract minority carriers such that they form a concentration of 10 power 15. But threshold voltage is a number, okay, and it is in particular a number, a voltage that is required to be applied at the gate terminal, and that is the amount of voltage when we are guaranteed of this channel region with significant amount of carriers. We discussed all this yesterday. Just having a few carriers is not enough for current. We need a large number. How much we need? That is given by this threshold voltage VT. So if I have VT amount of voltage, I can consider my transistor to be on. And as a result, or as a way in which the transistors are designed, NMOS transistor will have a positive number for threshold voltage, 0.4, 0.5, etc. PMOS transistor will have a negative value. We saw this case also. We need VGS equal to minus 2V. So some negative voltage will be required for the threshold voltage, and we saw the condition also where the transistors are considered on and off. So this much we saw yesterday. We started one question. So nice question, and it is directly related to current conduction. So I'll just do the same thing again for the sake of continuity. Okay, I'll write the full question and discuss the okay. So the question is, show okay, I think the last time the question was show the charge configuration for different values of VDS. We will do both VGS and VDS, different VGS and VDS for a NMOS transistor. Okay, make things a little simpler when we work with NMOS because it is the natural polarity with electrons. Holes are opposite. So first let us get familiar with electrons, then equivalently holes and electrons can be treated. Okay, so let us go with the first configuration. Okay, so let us also give a value for the threshold voltage, VT equal to 0.5 volts. So we have a NMOS where In the first case, okay, let us call this case A, 0 volts, okay, which means that source is connected to ground, drain is connected to 2 volts, gate is 0 volts. So VGS equal to 0 volts, right? 0 minus 0 is 0, and the VGS is lesser than VT. So the transistor is off. This is the electrical condition. Okay. Now what about the charges in this region? This is N plus, this is N plus. Nothing, no, absolutely no effect on the substrate region. No channel is formed because throughout it is almost at the same voltage. Okay, because this terminal is at 0 volt, and if you remember a p-type substrate, okay, the bulk is also connected to ground. So the difference between the voltage through the regions of the substrate is 0. Everything is at 0 volts. So there is no need for the holes to rearrange themselves. They are just equally distributed through the substrate region. So this is the configuration of the charges for this particular polarity. So next let us look at, okay, so I have a different electrical condition now compared to the first case. Both the source and the drain I am connecting to ground, and only the gate terminal I am connecting to 2 volts, positive 2 volts. So because this is positive, it is going to attract, okay, all the minority electrons plus some electrons from these two very dense regions are going to attract, and they are going to sit in this region. In this particular case, VGS equal to 2 volts, which is greater than VT. Okay, transistor is considered on because our electrical condition for NMOS transistors is VGS should be greater than VT, and it is true. So the transistor is considered on, okay, but because both the drain and source are at the same level, the current flowing through the transistor is 0. There is no current flowing because even though the minority charges are attracted, they are not moving. We need the charges to move for there to be a current. So there is no current flowing here, but the transistor is considered on. Okay, so this is the second case. Now what we will do is we will maintain transistor off. There is nothing else to see. It is off means it is off. I can keep changing this VDS. 2 volts can go to 0 volts, 2 volts can go to 5 volts. It can go to any value. The current will still be 0 in this case. So there's nothing much to see here. Here we will see a few different things. When the transistor is on, okay, we will try to slowly increase this side. One side will be at ground only. The other side we will slowly increase the VDS value and see what happens to this charge configuration. Thank you. Okay, sorry about that. Very strange. We are talking about you, but in the past, Madam was worried that there's no students joining, and she was thinking maybe I did something. I hope I didn't do anything that bad. Okay, so we'll continue with what we are doing here. So what I'm trying to say is, we are going to keep it on, okay, and slowly increase the drain voltage to see what happens here, and this will also tell us how we can get an expression for the current. Okay, so the next C. Okay, so 1 volt, we are giving 1 volt to the drain voltage, and since this is 0, VDS equal to 1, VGS equal to 2. So VGS is definitely still greater than VT, so it is on. Okay, this much is true. Now, before we look at the current, we can't calculate the current. There will be some current flowing for sure. Let us look at the charge configuration. This is important because, and I drew this diagram last time also. I'll just between this side, sorry, this diagram and this diagram. In here, the concentration or the charge concentration between the source and drain is the same. Okay, but here we see a slight gradient, and the reason for this is very simple. Okay, we discussed this last time also. Let's say that, let's use another example that will help you understand. Okay, let's say that you all go to all of you, A, B section, go to a hotel. Okay, and this is the hotel, and it's a buffet. So there's obviously many things. Okay, let's say that this side of the buffet is your rice sambar, and this side is the more exotic things like maybe um, continental food, maybe Chinese, all the other things are here. So all of you are entering and you think for some time, and obviously, right, most of the people will go inside here. So you don't see much crowd here because they're already inside the region where the good food is being served. In this region, you have to think a lot. So you don't want to go in here. So people are not going in here, they're waiting outside, and they rather go into the region where the more exotic food is being served. Exactly same thing here also. Why is there a gradient in this charge concentration? This side, okay, is connected to ground. Ground is not a very nice polarity for electrons because that is a negative. In this is the most negative voltage in digital circuits is ground. However, this side you see a positive 1 volt. So all the electrons that are attracted, okay, very quickly they go off into the drain region. They don't go very quickly into the source region because they don't like that particular region because of the polarity. So that is why you see a larger concentration outside the region compared to the drain region. That is why there is a gradient. There is a gradient in the concentration because this is a 1 volt polarity, which is a positive polarity. Before this was also 0, that was also 0. So all the electrons getting attracted, okay, they go in equal amounts to the source terminal and inside the drain terminal. So the concentration is the same throughout. But here, few of them go inside here. That is why you see a gradient in the concentration. And rate of change of charge. As I come in this direction, okay, there is a difference in the charge concentration. So then definitely I am having a current, and that is why IDS is not equal to 0. So now let us, we have a little bit more space. As you recall, in digital circuits, 0 to power supply. So power supply is 2 volts. So I can increase this little bit more. Let us go one more step all the way up to 2 volts, which is the maximum value for drain voltage also, and see what happens to the channel configuration. Okay, so I'll just erase this diagram. This is the case D. Okay, so now 2 volts, and this is continuing to be the same, 0 volts and 2 volts. Now we will see a new phenomenon. What happens is this reduces even more. Right now it is reduced compared to this. Okay, as we go all the way to 2 volts, it reduces even more to a level that even before the drain terminal, okay, the channel region stops to exist. It doesn't mean that there is an open circuit. Okay, many students, because of this diagram, it looks like there is an open circuit. That is not the case. What that means is any electrons that are attracted to this region, okay, very quickly they will jump off inside the drain region. They are not allowed to, or they don't want to stay in this region. Why is the reason? Again, now we have increased it to a higher value from 1 volt to 2 volts. So they don't have any doubt. Any electrons attracted to this region by this plus 2 volts, okay, they don't stay in this region because they see another plus 2 volts here and they jump into the drain region. And that is why in this very small region here, okay, we don't see any electrons collecting, and this particular point is called as pinch off point. Okay, and when the channel gets pinched off, it doesn't mean that it's open circuit. It just means that the very high drain voltage attracts all the electrons from the channel region into it. So no electrons are allowed to stay in this region. Okay, that is the only difference. And on the source side, no change at all. From this diagram to this diagram to this diagram, all are at 0 volts. The concentration remains the same. And another thing, now the concentration gradient, okay, very quickly. So first is we will write VGS on. Okay, we have not changed that condition. Again, IDS is also not equal to 0 because same reason, there is a concentration gradient. But another thing, if you compare diagrams C and D, okay, in which diagram is the concentration gradient higher? That is the rate of change of charge. Which diagram is it higher compared to C and D? Right? Definitely in D it is higher because on this side it is the same, but very quickly it is going to 0, which means this current somehow is going to be higher than current in C case. So this is one thing that also we will see when we come up with the equations. The current is highest in this particular mode of operation. So now that we have divided the modes of operation, we can also give them some names. This is very important. Okay, on is one mode. Definitely, if the on condition is there, only some current will flow. But in addition to on, based on this existing or not, that is whether pinch off has happened or not, we can look at two different situations. And this is the case where pinch off has not happened. Okay, this mode of operation is called as linear mode of operation. Okay, and this mode of operation is called as saturation mode of operation. So we can further distinguish between the on conditions. We are only looking at the on conditions. All these three diagrams, B, C and D, okay, the transistor is on. In that condition, because the channel is existing from the source to the drain, it is called as linear mode of operation. Linear mode of operation, the definition is what I just said. The channel should be through, the charge carrier should be through the channel region. Channel region should be from the source to the drain. If the channel region doesn't extend till the drain, okay, that means that pinch off has happened. That particular mode of operation is called as saturation mode. So based on that definition, this is which condition, linear or saturation? Just use the definition, right? The channel exists from the source to the drain. So this is also linear mode of operation. So this is the division that we are going to do in terms of the channel charge configuration, but channel charge every time is not easy to do. I don't want to draw the diagram. The easier way is through the voltages. We have these terminal voltages, right? If I can describe the conditions, that is linear or saturation, through the terminal voltages, that is much simpler for me. And the way we do that is here, okay, first of all, we are talking about NMOS transistor only now. The question itself says NMOS transistor. So whatever conditions we are talking about, linear saturation exists for both NMOS and PMOS. But since we are looking at electrical conditions, we are looking at NMOS only now. Okay, later on, once we finish everything, then we will look at the conditions for PMOS also. So VGS definitely greater than VT, that is a given. Otherwise, it is not going to be on. So that is not the condition. What other condition can I come up with where the transistor is either in linear or in saturation? And for that, we have to bring in the drain voltage, because the drain voltage, if it is low, okay, it is the lowest in this case. That is, it is at 0 volts, VDS equal to 0. So definitely channel exists till the drain terminal. Here, drain voltage has increased little bit, okay. The size of the channel on the drain side is little bit lesser, but the channel has not disappeared, it is still there. So here also channel is there, but here the drain voltage has still gone higher and the channel has completely disappeared from the drain side. So this drain voltage is a very important parameter for determining whether the transistor is in linear or in saturation. So the most important thing to remember, the electrical condition will come, but to remember for the properties of the transistor, if the drain voltage is low and the transistor is on, it is usually in linear mode of operation. If the drain voltage is high and the transistor is on, it is usually in saturation mode of operation. So we can list the conditions here. I will write them down. Okay, so I will erase this diagram, or maybe I will erase this middle diagram. Okay, so this is very, very important, this condition, because the current also, okay, we said it is not the same. It is lower in this, it is higher in this. So it is going to be slightly dependent on the conditions that we are listing here. So we look at NMOS. Okay, so one side I will write the simplest where VGS lesser than VT, NMOS off, okay, and what is the value of the current IDS? 0 ampere, nothing to do, okay. We don't have to calculate any current. There are certain currents flowing. Unfortunately, this is one of the problems of even MOS transistors. We said that we came from BJT to MOS because of the current conditions, but even in MOS there are some leakage currents, so we will not look at them for now, okay. In this course, IDS equal to 0 if the transistor is off. Now the other side, we are going to assume that VGS is greater than VT. It is on, okay. VGS greater than VT, transistor is on. Now within these conditions, we have two sub conditions for the linear and the saturation. So within this case, we are going to divide into the linear and the saturation. So remember always, when the drain voltage is lesser, it is in linear mode. So how does that come in the condition? VGS minus VT, okay, is greater than or equal to VDS. This is the linear region of operation, okay. That is VGS minus VT. Why this minus VT comes, we will talk about that a little later when we go into the derivation. But if this term left hand side is greater than VDS, okay, that is the drain voltage is low, it is the linear region, and this is for NMOS, okay. And the opposite, that is very simple, VGS minus VT this is the condition for saturation. VGS minus VT is lesser, or more conveniently for us, the drain voltage is now higher, which means that pinch off has happened and the transistor is supposed to be operating in saturation mode of operation, okay. So this is the two sub conditions within on. Both conditions, the transistor is definitely on, okay, linear and saturation. And from this, we will slowly go into the equation for the current, that is the current flow. What is the equation? And since we mentioned that the current is more, okay, also one thing to remember is that the current equation is also divided into the regions. First region, simplest, 0. For the linear region, if this condition is true, we are going to have one current equation, and if the last condition is true, we are going to have a different current equation. Fortunately, the derivation is almost the same, okay. 90% of the derivation we will do for the linear. The slight modification, we will just convert it for saturation. So it's not going to be two separate derivations, but the expression is different. What that means is, whenever you are going to calculate the current, which is what we will be doing, we have to find out what is the region of operation. Directly, if you put the current and calculate, you will get an answer, but it might not be correct because there are two separate regions and two separate equations for the current. And you might consider what is the border of these two. That is when pinch off just happens at the edge of the drain region. So if I redraw this such that the pinch off point coincides with the edge of the drain region, just for this is the border condition. That is when VGS minus VT equal to VDS. Okay, let's not worry about whether it's saturation or linear. According to that definition, it's in linear, but the transistor can be considered in either mode of operation. That is when we have applied the voltages such that VGS minus VT is equal to VDS. That is, the pinch off just happens at the border of the drain terminal. Okay, so these are the different modes of operation. Based on this, we will slowly try to derive an expression for the current. Very important part of this particular unit, this particular course. What is the expression for the current flowing through a MOS transistor? So we will remove all this. Okay, so MOS current, and like I said in the beginning, the equation for the current is, of course, from a practical perspective also it's very important, but the terms in the equation give us a very clear picture of how to increase the current. And why do we want to increase the current? Current is flowing, it will flow. If it is on, current will flow, right? But the problem is the current directly determines the speed. What is the meaning of that? Suppose you have a very small current, okay? Using that current, basically what is happening everywhere in digital circuits, seconds. So what is the effect of current in digital circuits? As such, we don't care about current in digital circuits as much as we care in analog circuits. Analog circuits, the current value, etc., is calculated because it might depend on some amplification, etc. We need current amplification, current mirror. All these things are more common in analog circuits. Digital circuits, current is flowing, it's a given, okay, and we don't want to control its value very exactly, okay, we don't have any amplification or anything, but the current determines the speed of the circuit. That is the main thing to remember in digital circuits, because in digital circuits, what is happening through the circuit, right? There are only two values of voltages, that is, it can be at 0 or VDD, any circuit, any node, anywhere in the circuit, right? And we are going to give one set of inputs and we will get the output. What is the output? Output is a voltage value. It is either 0 or 1, that is 0 or VDD. But the speed of operation of the circuit, right, is what that means is how fast can I give the next set of inputs. That is, I have a clock signal, right? and the clock signal will, every clock edge, one new set of inputs will be coming. So within the next clock edge, I have to calculate everything inside and keep the output ready. If that is not possible, that is, if I'm not able to do that, what is the meaning of that? Some particular output is not ready. That is the output, maybe it is going from 0 to 1, or it is going from 1 to 0. It is going from 1, say, which is 2 volts, for example, all the way to 0 volts. So it is going from 2, 1.8, 1.4, 1.2, 1, and then maybe when it's at 0.8 volts, the next set of inputs have come, and it's not at the correct value, because whoever is checking these outputs, they will see a value of 0.8. They won't understand what is 0.8 in digital logic. Is it 0 or 1? So it will be taken as a maybe a don't care, or it might be taken as a wrong value, high impedance value. All sorts of errors can happen. So that is not acceptable. So how do I make that part of my circuit faster so that it is able to go all the way from 2 volts to 0 volts before the next clock edge comes into the picture? And that is where the current comes into the picture. I have to increase my current, okay, so that the node is able to discharge faster. What is the meaning of 2 volts? Suppose I have 2 volts at some particular electrical node, okay. 2 volts means that there is some charge. This is the electrical charge. This is the electrical description of the node. This is the physical description of the node. There is some charge sitting on that node, okay. Maybe it is, say, some I don't know, whatever, say some 10 power minus 10 coulomb plus, okay, because it's positive. Now these are all positive charges. Definitely they are not protons. We don't have protons outside of the atom. This is positive charge in our, this thing just means that there is excess of holes compared to electrons. So we have to somehow remove that, right? And that is the meaning of discharge. So now this is at 0 volts. This is where the transistor and the current comes into the picture. Any circuit is going to be connected like this between the 2 volts and the 0 volt. So if the transistor current, which is what we are going to do, if the current is very small, then it takes a long time to go from 2 to 0. If the current is large, then very quickly it will go from 2 to 0. So that is why we need the value for the current expression to find out for this particular case. Now this is not one size fits all, right? Because this is 2 volts. That is more general, but more important is how fast do we need for this particular design, which has a clock of, say, 100 megahertz, right? Which means that in 1 by 100 megahertz, which is 1 by 10 power 8 seconds, or 10 nanoseconds, I want this to be completely discharged. So based on this particular requirement, we will set the current flowing through the transistor. Then the next question is, if something changes, suppose the clock frequency changes. So that is why we need to know what is the value for current before we can design this circuit. That is the whole thing of digital design. Okay, we need to design the circuit, not just the transistor, but also the configuration, so that we can meet all the requirements of the functionality. So this is a general description of how the current is important in digital circuits. Current is not something that we deal with too much in digital circuits. We are just worried about whether it's high enough for my functionality. If it is not high enough, how can I increase it? So when we have to increase it, we need to look at the expression for the current. So that is the first thing we will do. Derive an expression for the current flowing through the transistor. Okay, so for any derivation, generally, I'll just write this in the side. What is the outline of this particular derivation? That is, what are the large steps? This is also very useful for you to remember this derivation. If you can just divide it into 2 or 3 big blocks, and then each sub block has some steps, right? This is also the same. So first, we are going to use Remember the equation from maybe second PU even, Q equal to CV, maybe in even earlier, maybe 10th standard, 12th standard, whenever you have studied the definition for a capacitor, you have learned this particular equation. What is the charge stored in the capacitor is given by C into V. So here also, okay, we are going to start with this expression. Remember that the gate is responsible for attracting all the charges. So how much charge does the gate attract? That is given by Q equal to CV. In particular, QC, which is the channel charge, equal to C oxide. Now, where is this capacitance suddenly coming from? If you remember, the gate is separated from the substrate. Okay, gate and the substrate, these are my two parallel plates of the capacitor, and in between those two is the oxide region. Oxide region has some capacitance that is given by C oxide. And the voltage, what is the voltage between the two plates? We will call that as V gate or V gate channel. This is something that we will use for now, and once we go into the derivation, we will change that to a more suitable form. Okay, this is the first thing. The gate terminal is responsible for attracting the channel charges to the channel region. Once that is there, then how do we calculate the current? So if you remember in the previous class also, the current is due to an interaction of two electric fields. One electric field, which is the gate, is responsible for attracting the charges towards the channel region. The other electric field is a horizontal electric field. So if you remember in case D, there was no drain source voltage. But even even though the gate was on, the drain source voltage is not there, the charges will not flow, current is zero. So that particular this thing, I okay, let's leave it at this point. Okay, dq by dt. This is the second part of the derivation. Once we get the actual value for the charge, we will see what is the rate in which the charges are moving, and somewhere here qc is the same as this. Okay, and t is the time, and somewhere here the horizontal electric field or the drain source voltage VDS is responsible for the horizontal electric field that will come into the picture. So this is the overall outline. Okay, so let us look little more detail at each of these blocks and get the overall expression for the current. So first start with that one. Okay, Q Cox into V gate. So first let us look at Cox. This is the general expression for capacitance A epsilon naught by D. In particular, in our case, okay, A is given by the area of the transistor. Where is the transistor now? Let us draw the three-dimensional diagram. Okay, so this is not complete, but this is the gate. Okay, and the gate is sitting on top of the substrate. In particular, it has a width W and a length L, which means that the size of the parallel plate or the area of the parallel plate. This is one parallel plate, the gate terminal. The below is the other parallel plate, the substrate terminal. So what is the size of the parallel plate? It is nothing but the size of the gate terminal, which is given by W into L. It is a rectangle, right? And into, now this is something that you have to remember. Generally, it might be given. If it is not given also, you can remember epsilon oxide, okay, is 3.9, the relative permittivity of the thin oxide. There are two different materials here. The bottom is a silicon substrate, right? But we are not talking about the silicon substrate when we are talking about the capacitor. The capacitor is separated by a material. This is one part of the capacitor. The bottom silicon itself is the other parallel plate. So what is the material that is separating them? That is the epsilon oxide, and you have to remember that its relative permittivity is 3.9 if it is silicon dioxide. Now we have also come to some more modern materials like hafnium dioxide, where the relative permittivity is higher. Okay, it's about 23 or 24, and the reason is this oxide, right? This D, okay, which is the oxide thickness. Because the permittivity was low, the oxide thickness became very, very small. It started shrinking almost to the size of 2 nanometers. When it went to that level, what started happening was the leakage current. We said that the oxide, silicon dioxide here, is responsible for the insulation of the gate terminal. That is true. But the problem is when the thickness was so low, right, it started becoming very difficult to control current in this direction. So some people, what they have tried is they have increase the thickness again, okay, instead of 2 nanometer, maybe go to 10 nanometer. But to get the good control, they have shifted the silicon dioxide to different material, in particular the chosen material. It's not very easy to randomly choose a material, because in the fabrication, which is a very, very complicated process, all the components have to be adjustable with each other. The silicon or whichever has to accept whatever you are putting on top of it. If it doesn't like it, then you can't make the transistor only. So after a lot of research, they found that hafnium dioxide was working well. So some people make it, but let's not worry about that. Okay, in most cases for us also, it is still going to be silicon dioxide. If it is not given, number one, the relative permittivity is 3.9. Okay, and into 8.9